Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is part 3 in a 4-part sequence on classification and discrimination. It's intended for the course Analytic Methods for Lawyers, but my hope is that I've described it in a way such that it's accessible to non-lawyers. If you haven't looked at the prior 2 videos, I would urge you to do so before tackling this one, and I'd also urge you to brush up on your understanding of classifiers generally and of confusion matrices and their statistics. In this essay, I'm going to look at how various notions of justice affect the false positive rate, true positive rate, accuracy, and classification thresholds for various groups. To get there, I'm going to develop formalizations of inaccuracy costs, a relationship between false positive rates and thresholds, and various justice constraints. I'm then going to show how inaccuracy costs can be minimized under these various justice constraints, and then determine the optimal threshold. I'm going to start with a sample scenario, work through that, and then I'm going to generalize the process so that I can run a number of experiments that highlight pretty precisely what actually causes the discrimination that appears to result in many of them. Basically, I'm going to create a framework from which issues of classifier discrimination can be explored. I'm also going to show with this method the additional inaccuracy costs created in the effort to relieve the discrimination resulting from the inaccuracy cost minimization unconstrained by various notions of justice. There are serious implications of the methods shown here for understanding affirmative action programs in which different thresholds might be used for different groups. This video is going to be long and somewhat complex, so I thought I might provide an executive summary at the outset. Point 1. The ratio of false positive costs to false negative costs, the cost ratio, coupled with the incidence of the positive class, determines the inaccuracy cost minimizing false positive rate and, derivatively, the optimal threshold. Finding 2. The higher the incidence of the positive class, the greater will be the optimal false positive rate, meaning the lower the optimal threshold. Finding 3. The higher the ratio of false positive costs to false negative costs, the lower the optimal false positive rate, meaning the higher the threshold. Finding 4. Accuracy is maximized at the same threshold that minimizes inaccuracy costs, with the cost ratio set to 1. Number 5. The discrimination, in air quotes, created by classifiers is predominantly the result of their different ROC curves among different groups. And that discrimination will exist even if the underlying incidence of the positive class in the groups is the same. The discrimination gets stronger if the underlying incidence of the positive class among the majority is closer to an extreme, such as 0% or 100%. Finding 6. In the scenarios considered here, the costs of inaccuracy in classification do not usually increase greatly with most requirements for various forms of equality. But requiring a classifier to produce both the same false positive rates and true positive rates among groups can greatly increase inaccuracy costs, particularly where there are many recognized minority groups for whom a classifier may lack the data or sample size that leads to good performance. All right, let's start right up. Let's start by developing a function that's going to measure the inaccuracy costs of our classifier. Let me just motivate it with a concrete example. Here's a confusion matrix that's been normalized so that the total of all the values is 1. Now, suppose the cost of a false positive is 2, and the cost of a false negative is 1. Well, there are 0.1 false positives, so the total false positive cost is 0.2. 2 times 0.1. And there are 0.3 false negatives, so the total false negative cost is 0.3 times 1, which is 0.3. And 0.2 plus 0.3 is 0.5. So the cost of inaccuracy is 0.5. All right, that wasn't too bad. Now let's do the same computation, but this time with only 3 pieces of information. The false positive rate, the true positive rate, and the incidence of the positive class. You can see the false positive rate is 1/3, the true positive rate is 4/7, and the incidence is 0.7. The number of false positives is the product of 1 minus the incidence, that's 0.3, and the false positive rate, which is 1/3. So it's 0.3 times 1/3, and each false positive costs 2. So to write a little formula, the total cost of the false positives is 1 minus the incidence multiplied by the false positive rate multiplied by the false positive cost, which here is 0.2. Now the number of false negatives is the product of the incidence and 1 minus the true positive rate. We're given the true positive rate, 4/7, but what we need to find out is what is the false negative rate. And so that's basically 1 minus the true positive rate. So what we get is the incidence, 0.7, the false negative rate, which is 1 minus 0.4 divided by 0.7, and we have to multiply that actually by 1, the cost of the false negatives, and so we get a total of 0.3. And so the total cost of inaccuracy is again 0.5. We just computed it in a slightly different way. All right, so let's write that as a function. The inaccuracy costs are a function of the cost, the false positive cost and the false negative cost. The positivity rates, the false positive rate and the true positive rate, which I'm going to collectively refer to as gamma. The incidence, and I'm going to have the option, I don't even think I ever use it here, but I reserved myself the option of saying, well, what if you have 100 people in the group? So you could just multiply everything by 100. So we compute that as a dot product. It's the costs, that's FPC and FNC, multiplied by the number basically of people who are false positive and false negative. And that is, here's our incidence vector, and then we've got this little piece of code is designed to turn the true positive rate into a false negative rate. That's what's going on here, and so that's our formula. Now let's see if we can develop some intuition about how those inaccuracy costs vary as we move along the ROC curve. To do that, I'm going to need an actual functional form for the ROC curve. And actually, after playing around with some real data and using symbolic regression, for those of you who watched that video or read that essay, I actually used symbolic regression here to find a functional form that met the requirements and also seemed to be consistent with the data. So here it is. Here's the basic expression. FPR is the false positive rate, and A is a parameter that you want to use. In general, you want A to be greater than or equal to 1, and the higher A is, the weaker the classifier is. So just so you get a flavor of how this all works, I'm going to have a manipulate here in which I'm going to plot the ROC curve and see how the curve varies as we change the parameter A. I'm also going to compute the area under the curve, which we've studied before, which is a metric of how well the classifier is performing. So here's A is, I believe this is 1, and actually let's do something here. Let's make it so you can actually see the value of the parameter. There we go. And as I increase the A parameter, you can see that the ROC curve starts shrinking towards that 45-degree line, and also the area under the curve statistic starts to decline. So this just gives you a feel for a low parameter in this instance leads to a very accurate classifier. A higher parameter leads to a less accurate classifier. So I've just managed to come up with a parameterization of ROC curves. I'm now going to create two special ROC functions that I'm going to use throughout this video. One for group 1 and one for group 2. And you'll notice that the parameter for group 2 is higher, 1.2, than it is for group 1, 1.08, and that's to represent the idea that the classifier, for whatever reason, is performing better generally on group 1 than it is for group 2. So let's make sure that Mr. Wolfram knows about that. And now let's actually take a look at our inaccuracy costs, where the cost of a false positive are 2, the cost of a false negative are 1, just like before. The incidence is 0.7. And we're going to use parametric plot 3D, which is going to trace a curve in 3 dimensions in which the x-axis is the false positive rate, the y-axis is the true positive rate, so we've got the makings of an ROC curve there, and the z-axis are the corresponding inaccuracy costs. This iconized away code is basically cosmetics for the parametric plot that's going to color the curve according to the inaccuracy cost values. And so you can see that the inaccuracy costs seem to be minimized as the false positive rate is, I don't know what that is, 0.5-ish, and it goes up from there. We could also look at this same curve from above. This is exactly the same code. The only thing I've changed is to say look at it from on high. So when we do that, we see this looks like an ROC curve because basically we can no longer see the inaccuracy cost information. All we can see is the coloration of it. And again, I don't know where it's maximized. Maybe we'll ask it. In fact, that's what I do next. I say, let's use and minimize to find the value of the false positive rate that minimizes the inaccuracy costs, subject only to the constraint that we can't have false positive rates that are less than 0 or greater than 1. All right, so let's do that. And it turns out that the false positive rate that optimizes this is at 0.329. All right, I could buy that. How else could we see that? Well, here's another way we could do it. Let's generate a 2-dimensional ROC curve, the kind of thing that's generally presented. That's what this code is doing here. But then overlay on top of it a contour plot of the inaccuracy cost. And a contour plot is just it's a map in which the lines on it show equal values of this expression. So in this instance, we're going to be showing equal values of inaccuracy costs. And the rest of this is just cosmetics that maybe I should have iconized away, but there it is. All right, so here's our ROC curve, and then each of these lines here represents equal inaccuracy costs. As it happens, the inaccuracy costs decline as we go this way. That makes sense, right? If you have a true positive rate of 100% and a false positive rate of 0, you're going to have 0 inaccuracy costs. Whereas if you have a false positive rate of 1 and a true positive rate of 0, that's a nightmare, and your inaccuracy costs are going to be very high. So we can find the optimal spot by looking at where one of these contour lines is just tangent to the ROC curve. It looks like that happens right about there, and right about there, if I drop it down and I cheat a little bit, is obviously 0.32915 right there. Okay, so let's generalize these diagrams and consider the inaccuracy costs as we vary 2 factors. Factor one is we're going to vary the cost ratio. That's the ratio between the cost of that's not right, a false positive costs and a false negative costs. And I'm also going to vary the incidence of positivity in the group. So let's save that change. Let's now look at this. Here's my manipulate, and you'll see I'm permitting myself to change the cost ratio, and I'm permitting myself to change the incidence. All right, and so what we see is, as we change the cost ratio, the lines of equal inaccuracy change in slope, and so as I increase that cost ratio, you can see, I think, that the point of tangency is going to move down and to the left on our curve. So right now, I don't know, it might be about there, whereas if the cost ratio were considerably lower, like that, it might be all the way up here. Similarly, I can change the incidence. As I increase the incidence of the positive class, I tend to want a point higher up on the ROC curve, representing a higher false positive rate, and that means that the threshold is going to be lower. How am I going to get a higher false positive rate? I'm going to say it's easier to be classified as positive. So again, this is giving you, I hope, some intuition about how classification is affected by different ratios of false positive costs to false negative costs and the incidence of positivity in the underlying class. If you'd like and you're good at visualizing three dimensions, we can also look at a three-dimensional version of this. And you can see how changing the cost ratio is moving that three-dimensional curve around, and how incidence is moving it around. And again, if you want to see this orthographically from above, you can just click that. And now if you move the slider, you're going to see what's interesting is that actually in 2 dimensions, the ROC curve doesn't change. Okay? All that's really changing are the inaccuracy costs corresponding with these points on the ROC curve. The ROC curve is determined by the classifier itself, not by the costs of inaccuracy or the incidence of positivity. But if you look at it in 3 dimensions, come on, in 3 dimensions, then you should, let's redo this. Yeah, I'll have to figure out that bug. You can see the curve wiggling about as in 3 dimensions as we change the sliders. So I hope what you're seeing is that, at least in this example, the optimal false positive rate increases with the incidence of the positive class. And since the false positive rate is inversely related to the threshold, the optimal threshold decreases with the incidence of the positive class. As I say, if you want to reduce error costs, the more positive people there are, the more you should classify people as positive. There. I also hope you're seeing that the optimal false positive rate decreases the higher the cost ratio, i.e. the ratio of false positive costs to false negative costs. And since the false positive rate is inversely related to the threshold, the optimal threshold increases as the cost ratio increases. The more it costs to falsely designate a negative person as positive, the more we want to be certain before we designate a person as positive. Now, these were just illustrations. Maybe what I'm saying isn't true in the more general case. So let's bring in some calculus to get some greater assurance. And for those of you who aren't comfortable with calculus, you could bypass this section, but really, I'm going to make it so that it isn't too hard, or at least that's my goal. All right, so the first thing we're going to do is we're going to figure out where the derivative of inaccuracy costs with respect to the false positive rate is 0. And it's a good chance, if our function is nice, that that will be a place that minimizes inaccuracy costs. So I'm going to use algebra then to figure out, to solve, when is that derivative equal to 0. All right, so let's do that. And we get some expression here. Now, we could spend time figuring out what the heck that expression means, but actually we don't need to. It's just an expression. Let's hold on to it. Now what I want to do is I want to take the derivative of this expression, the value of the false positive rate at which inaccuracy costs are minimized, and take the derivative of that with respect to incidence. And so we should be seeing how does incidence affect the optimal false positive rate. So here's what we get. Well, this is an even uglier expression. But all I really care about is what the sign of this is. Is this positive or negative? And that we could figure out. Here are some facts that we know. Incidence is positive. One means positive and -1 means negative. The cost ratio is positive. We have no negative cost. You never get a benefit from classifying a person wrongly. And then the other thing we know is that the sign of the second derivative of the ROC curve is negative. Why is that? Because it tends to increase at a decreasing rate. That's maybe the one tricky point here. All right, but let's bring in our facts that we know. And now let's ask Mr. Wolfram to figure out what is the sign of the derivative of the incidence, is the derivative of the minimum false positive rate with respect to the incidence, plugging in, remember that's what /dot means, the facts we know. And it comes up with a nice clean result, 1. That means that the optimal false positive rate increases as the incidence increases. And since the threshold is inversely related to the false positive rate, the optimal threshold decreases as the incidence increases. We can actually do the same thing to figure out what effect the cost ratio has. Let's grab this expression here. I'm sorry, grab this expression here. And let's differentiate it with respect to the cost ratio. All right, we do that. Again, who the heck knows what that means? But we don't really need to know what it means. We're just trying to figure out its sign, and we're going to add one more fact to the facts we know, and that is that the sign of 1 minus I is also positive. Why? Because the incidence is always greater than 0, and so the sign of this value is going to be positive. And now let's compute the sign of this yucky expression, and we're just going to plug in the facts we know, and maybe we'll get a nice clean answer. And we do, -1. This means that the optimal false positive rate decreases as the incidence increases. Just what we saw on that when we were playing with the manipulate above. And since the threshold is inversely related to the false positive rate, the optimal threshold increases as the cost ratio increases. So we're now getting some of the physics of classification under our belt. Another factoid. Accuracy is maximized at the same threshold that minimizes inaccuracy costs when the cost ratio is set to 1. Right, so let's prove that. Here's our expression for accuracy of the false positive rate and the true positive rate and the incidence. It's how many people are true negatives? Well, the true negatives are 1 minus the incidence times 1 minus the false positive rate. And how many true positives are there? Well, it's the true positive rate times the incidence. So there's our accuracy. Now, let's differentiate this expression with respect to the false positive rate. All right, a little bug in the code is about to be fixed. ROC, see how it's black? That means it's defined. I don't really want it to be defined. I want it to be abstract, so let me just change it to R. All right, there we go. There's the derivative of accuracy with respect to the false positive rate. Now, let's find the derivative of inaccuracy costs with respect to the false positive rate. And let's stare at these two things. They're exactly the same. So that's my proof. All right, accuracy is maximized at the same threshold that minimizes inaccuracy costs when the cost ratio is 1. Let's talk about thresholds. You remember in the first essay that I talked about how the ROC curve that we usually see is actually a two-dimensional projection of a three-dimensional object. It's a curve that traverses a space with dimensions of false positive rate, true positive rate, and threshold, x, y, and z. What this means is there's a relationship between threshold and false positive rate. Or we could view it the other way, of a relationship between the false positive rate and the threshold. Supposing that relationship is as follows. The threshold is a function of some parameter a, which creates a function, which is a function of the false positive rate, and here's the form. How did I find this crazy form? Again, thank you, symbolic regression. All right, so let's get it in there. And now, let's take a look at what the relationship is. What does this function actually look like? All right, and so what you can see is that if the parameter value is relatively low, then there's almost a linear relationship between the threshold and the false positive rate. As I start to increase that parameter, though, it gets even more linear. Okay? If I start to get up here, that's almost indistinguishable from a straight line. So how bowy it is depends on how low this parameter a is. And these are what we're going to be playing with in the experiments to follow. And so suppose that group 1 and group 2 have different threshold functions. For group 1, it's t of 10, which I believe is about out here, almost a line. And for group 2, it's t of 1. And once again, I think we would benefit from an appearance goes to labeled addition to the manipulate. All right, so I happen to have nailed it. Here's what it looks like for group 2, and here's what it looks like for group 1. Okay, so we've done that. Okay, so far we've been looking at the relationship between ROC curves and inaccuracy costs and trying to find values on a ROC curve that minimize inaccuracy costs. But if we have two groups and some concern about justice, we might want to place some constraints on where those classifiers can operate. Maybe we feel it's unfair, for example, for two groups with the same incidence to have different true positive rates. That means that people who are equally qualified will not be classified as positive at the same rate. So let's explore some of these constraints, and I'm just going to give us some basic code to begin with. This is going to create a little legend. I'm going to keep using that legend, so I assigned it to a variable. And now let's look at our ROC plots for group 1 in blue, group 2 in red. And you can see that the ROC curve for group 2 is lower than it is for group 1. It's just not as good a classifier when it's working with group 2. Maybe there's data that's particularly relevant to group 2 that we didn't bother to collect. And we maybe don't need that data to classify group 1 accurately, or maybe there just aren't very many people in group 2, which is going to hamper the classifier's performance. For whatever reason, group 2 has a lower ROC curve. All right, let's find the optimal false positive rate and true positive rate, and derivatively the threshold for each group. And the way I'm going to do this is I'm going to use the nminimize command. I'm going to say minimize the inaccuracy costs. I'll come to this in a moment. Subject to the constraint, that's the second argument, and the only constraint I'm going to impose here is the rather boring constraint that the false positive rate has to be between 0 and 1. What's the rest of this stuff? This is telling us that the false positive cost is 2, the false negative cost is 1. This is telling us that the incidence is 7/10, and this is telling us to use the ROC curve for group 1. So let's do that minimization, and we find out that the thing that minimizes inaccuracy costs is for the false positive rate to be set at 0.23749. Well, let's do the same thing for group 2. Everything's the same, except we're just using the ROC curve for group 2. Otherwise, everything's the same. And we find that does make a difference, that now the optimal false positive rate is higher, 0.329. So what does this tell us for thresholds? For thresholds, what we can do is we can say, hey, what is the threshold, given T1, at this number, 0.23749. Why is that this 212 business? It's because we take the second part, and there's only one part to the second part, and then we take the second part of that. So that's what that 212 idiom is about. We do the same thing for group 2, and we find out that actually the optimal threshold in this instance for group 1 should be higher than it is for group 2. In some sense, group 2 gets some affirmative action here to compensate for the lower ROC curve on which it operates. And personally speaking, I think that's an interesting finding, is that we're doing affirmative action here, not because of any concerns about social justice or diversity or all the usual things that are trotted out, but actually just to have a more accurate classification of individuals. We can also show on this diagram where we lie. So we can see that if we do it this way, the false positive rate is higher for group 2 and the true positive rate is lower. Well, we could also figure out what is the total inaccuracy cost under this regime where we get to set the thresholds independently for each of the groups. We get to set the false positive rate independently for each group, and our only goal was to minimize inaccuracy costs. So let's see what we get. We get 0.296587. So just hold that thought. You also might be wondering, gee, I wonder if this seems like a kind of strange result. I wonder if it's an artifact of his decision to use asymmetric cost ratios, where it's 2 for false positives and 1 for false negatives. Let's just run the same experiment. Everything's the same, except that now the false positive cost is 1 and the false negative cost is 1. We have symmetry. And I do it, and the answer is nope. The thresholds for the groups, the optimal thresholds, are still quite different, and so our finding about the desirability of different thresholds did not depend on this asymmetry of false positive costs and false negative costs. All right, well, one notion of justice might be that the false positive rate should be uniform among both groups. If a certain percentage of unqualified people who actually will fail, are being classified as positive in one group, then the same fraction should be classified as positive in the other group. So let's actually see what happens in that scenario. Here are our total inaccuracy costs, 80%, because we have 80% in the majority group, times their inaccuracy costs using their ROC curve, plus 20% of the inaccuracy costs of the second group, which we're going to compute using their ROC curve. So it's a weighted average. And the only thing that's happening here is the false positive rate has to be the same for both groups. I'm not going to permit different false positive rates to be used. I will constrain it to be between 0 and 1 because that's the only thing that's sensible. And let's see what the optimal false positive rate is. So the optimal uniform false positive rate is 0.253019, which is lower than it was for, I'm sorry, we have to go up here to these values. It is higher than it was for group 1 and lower than it was for group 2. Okay? We could also say, hey, what's the threshold on these settings? And so here's that 212 metaphor to extract out the false positive rate value. And it turns out again that the thresholds are different even though we've required that the false positive rate be the same, and that's because they are operating on different threshold relationships between threshold and false positive rate, possibly due to differences in calibration of the classifier working on the different groups. All right, we can visualize this. Here's a little bit of visualization code here, making arrows, making lines, and let's construct a graphic. And you can see here that the imposition of a false positive rate tells group 2 to move down its ROC curve somewhat substantially, and it tells group 1 to move up its ROC curve just a little bit, and that way they're both operating on the purple dashed line where their false positive rate is the same. Why is group 2 moving more than group 1? Because group 1 has a lot of people in it, and so a little movement has a bigger effect than when group 2 moves. Okay, now let's look at 4 metrics of equality, or if you prefer, justice. And I'm going to refer to these notions following the work of some leading scholars. I'll call them demographic parity, equal opportunity, equal odds, and the last one, I guess, is my own name, which is threshold equality. So what are these and what effect do they have on the inaccuracy cost minimizing solution to this classification issue? Demographic parity means that the positive rate should be the same for both groups. If 83% of group 1 end up being classified as positive, then 83% of group 2 should end up being classified as positive. It should be the same among both groups. So let's solve for this algebraically. Here is the positive rate for group 1. This is basically 1 minus the incidence times the false positive rate plus the true positive rate multiplied by the incidence, and that should be equal to the same idea for group 2. We're going to constrain our false positive rates to both lie between 0 and 1, and we're then going to solve for the values of the false positive rates that equilibrate the positive rate. And this is just saying, hey, could you please remember that the false positive rate lies between 0 and 1, otherwise we get weird stuff. All right, so this is the relationship between the false positive rate for group 1 and the false positive rate for group 2 that will result in demographic parity and the positive rate being the same. This expression is ugly, you don't really have to pay attention to it, but there it is. So let's actually plot the relationship though, and I'm just going to decorate my plot with a 45-degree line that I'm going to use all the time. So I'll just, instead of having to keep writing this code, I'll just write 45-degree line. So I'm now going to plot that expression as FPR1 goes from 0 to 1, a little bit of labeling and decoration. And here's the relationship between the false positive rate for group 1 and the false positive rate for group 2 that results in demographic parity. And so you can see that the false positive rate for group 2 is generally going to need to be higher than it is for group 1. Okay? What else could we do? We could also look at what's the relationship among the thresholds that creates demographic parity. Here's our expression for the threshold for group 1 with its false positive rate. And here is the expression for the threshold of group 2 with its false positive rate, although its false positive rate is a function of the false positive rate for group 1 that we saw up here. Isn't Wolfram language fun? And here we are. So what we see is that demographic parity requires the threshold for group 1 to be considerably higher most of the time than for group 2. And so in this scenario, at least, demographic parity would call for what we might call in the United States affirmative action. Okay, next justice metric, equal opportunity. Equal opportunity means that the true positive rate is equal for each group. The idea is, look, if you've got someone who's going to be successful, then the rate at which you classify those people as successful should be the same regardless of what group they're a member of. All right. So let's actually see if we can figure out what the relationship between false positive rates are in order to generate equal opportunity. So I'm going to say the true positive rate for group 1 should be equal to the true positive rate for group 2. Here are some sensible constraints. Find me the values of false positive rate 2 and false positive rate 1 that do this. No complex numbers in analytic methods for lawyers, and a reminder that please, the first positive rate has to be between 0 and 1. And we get a less icky algebraic expression. We could plot it, and we could see that equal opportunity is going to demand that the false positive rate for group 2 be higher than it is for group 1, which is reciprocally going to mean, as I show you here, that the threshold for group 1 is going to need to be higher than it is for group 2. So equal opportunity, again, is going to have that affirmative action flavor to it, at least in the scenario that we've been setting up here. The next metric is the sort of the toughest one. It's equal odds, and it says not only do we want the true positive rate to be equal, we also want the false positive rate to be equal. This is sort of a combination of equal opportunity and false positive uniformity. And let's see what that does. So here we're going to say, look, let the false positive rate for group 1 be the same as the false positive rate for group 2, and let the true positive rate for group 1 be the same as the true positive rate for group 2. Find me the values of the false positive rates that accomplish this, and what we're going to find out is either we basically have to have 100%, a threshold of 100% that nobody meets, or a threshold of 0% that everybody meets. So that's not very helpful. What we need to do in order to achieve equal odds is actually to get group 1 to move down to group 2's ROC curve. And if you remember the previous essay, I spent a good deal of time talking about how to do that navigation, either by random result flips or by stochastic thresholds. And the reason I spent all that time in the prior video discussing that was precisely because I knew we were going to need it here in order to achieve the equal odds metric that some people support and is certainly worth thinking about. So what we can do is to look at the differential thresholds that are going to be engendered by equal odds. Okay, let's look at that. And what you see is that in equal odds, the threshold for group 1 is going to be higher than the threshold for group 2. And let me just see if I can be maybe a little more clear about what's going on with equal opportunity. Equal odds. In equal odds, in order for there to be equal odds, basically, group 1 has to be operating somewhere on group 2's curve, because group 2, you can never go higher than your ROC curve. Otherwise, it wouldn't be the ROC curve. You can only go down through random flipping, weakening the classifier, stochastic thresholds, data blurring, and whatever else I said in essay number 2. And so in order to achieve equal odds, our friends in group 1 are going to have to use one of those methods to get down to the ROC curve for group 2. And so that's going to require some pretty major changes in the way that group 1 operates. Another notion of justice is threshold equality. Threshold equality means that the threshold used to determine who's classified as positive should be the same regardless of group membership. If it takes a probability of success greater than 57% to be classified as positive for group 1, then it should take a probability of success greater than 57% to be classified as positive for group 2. The system should basically be group blind. So let's see how that works in our setup. Here's the algebra. It's fairly simple. The threshold operating at the false positive rate for group 1 should be the same as the threshold operating at the false positive rate for group 2. And let's figure out the value of the false positive rate for group 2 that satisfies that. We get one of those little algebraic equations. We can graph that. And we can see that in order for this to happen, for threshold equality, at least in our scenario, the false positive rate for group 1 has to be higher than the false positive rate for group 2. We can also look at what implications are for the true positive rate. So here I'm just substituting in the equilibrating false positive rate that we found right here. And we find that the true positive rate for group 1 has to be a lot higher in our scenario than it is for group 2. So that if we insist on threshold equality, what we're going to see is a somewhat higher false positive rate among group 1 and a considerably higher true positive rate among group 1. And many people might think that's unfair, because this is all constructed with the incidence of positivity in both classes being the same. And yet, without any malevolence here, just as a result of, as we'll see, it's mostly the result of the ROC curve for group 2 being lower than it is for group 1, the members of group 1 are being treated much better by the classifier. Okay, so we've looked at the effects of these different ideas of justice on the false positive rate, true positive rate, and threshold of the classifier. But now let's look at what the effect is on inaccuracy costs, because we certainly might care about that. So let's start again with demographic parity. And here's our objective function. Here's what we're going to try and minimize. We're going to try and minimize the total inaccuracy costs. What are the total inaccuracy costs? They're 80% of the inaccuracy costs for group 1, because they're 80% of the people, times 20% of the inaccuracy costs for group 2, because they're 20% of the people. And here, everything else is kind of as it's been before. I'm using the false positive costs being twice the ratio, twice the amount of the false negative costs. I've got my incidence for both groups equal to 0.7. So there's our objective. And now let's set up our constraints. We have some standard constraints. We're going to be using these every time. So what are they? Well, the false positive rates and the true positive rates for both groups have to be between 0 and 1. Group 1 can't get above its ROC curve, and group 2 can't get above its ROC curve. Okay, so those are the standard constraints. Now I'll add in a special constraint. This is the demographic parity constraint. And here it is. This is the positivity rate for group 1. This is the positivity rate for group 2. We need them to be equal. Now I'm going to say, hey, Wolfram, minimize my objective function, total inaccuracy costs, subject to the standard constraints and the demographic parity constraints. And I want answers out for the values of the false positive rate for group 1, true positive rate for group 1, false positive rate for group 2, and true positive rate for group 2. And we did it. All right. So if we look at this number, 0.296646, and we hearken all the way back to when we computed the unconstrained accuracy, it was 0.296587. And so what we're seeing is that we didn't really, imposing this constraint of demographic parity in this particular instance, didn't change the total inaccuracy costs very much. We almost get it for free. I guess here's something that I could have shown you without all that scrolling. Partly this is because the positive rates were fairly similar to begin with, or they were similar to begin with. So here's an instance where one notion of equality in this scenario does not have a side effect of increasing inaccuracy costs. All right, well, what about equal opportunity? Equal opportunity, here's the constraint. The true positive rate for group 1 has to be the same as the true positive rate for group 2. And now we just want to minimize our same objective function subject to the standard constraints and the equal opportunity constraints. Same thing. So we do that, and we see again, there in this particular instance, it doesn't cost too much to get us to equal opportunity. Right? What about equal odds? Well, here are the equal odds constraints. The true positive rates have to be the same, and the false positive rates have to be the same. So let's minimize our objective function subject to the standard constraints and both of these equal odds constraints. Ooh, 0.37. So what we see is that equal odds, unlike our other measures, in this instance imposes substantial increase in inaccuracy costs. Why is that? That's because group 1 has had to move well to the interior of its ROC curve in order to achieve the equality metric. And so you ought to think about that. Because right now I've considered only 2 groups, but what if there were 4? Or what if we're concerned about intersectionality? That is, perhaps the ROC curve for group 2, maybe on balance, isn't too far below that of group 1, so that moving down to the group 2 ROC curve wouldn't be so great. But you could imagine a situation in which really group 2 is a composite. There's sort of group 2A, where the ROC curve is okay, but group 2B, where it's really rotten. And if we consider group 2B to be a relevant group, then we're going to have to drop the ROC curve for group 1 and for group 2A down to that low value, and we're going to get a great increase in inaccuracy costs. We're going to sort of sink to the performance of the classifier on its least successful group. And that, although it might be just, does result in pretty high inaccuracy costs. How do we actually make this movement down? Well, you remember in the last lecture I talked about random flipping, and we can actually compute what that random flip is. And with a little code bug repaired, we're able to do the algebra here. We're going to start with that equation or expression from the last lecture showing where you end up as a result of flipping alpha percent of those who were previously classified as negative and omega percent of those who were previously classified as positive. So we end up with this equation, which we can now solve. And it turns out that we need to flip 15.5% of those classified as negative, and 11.3% of those classified as positive. The other way we could get down to that ROC curve would be to subject members of group 1 to a random selection from two thresholds. Here, this is basically what we're going to need to have in order for this to work out. And so what we're going to do is we're going to try to find examples where this relationship is satisfied subject to these constraints. P is the fraction of time that you're subject to the lower false positive rate value, FPR11, as opposed to the higher one of FPR12. We're going to run that. It finds a bunch of possibilities. Maybe 18% of the time you're subject to this very, very low first false positive rate and whatever the associated threshold is, and the remaining 81% of the time you're subjected to this higher rate, or any of these things here. So there are lots of ways of dropping down. Is one of those ways better than another? Well, if it were me, I would want the difference in the thresholds that were going to be used, depending on the result of some random choice, to be minimized. So what I'm going to do here is to say I want the difference in the false positive rates to be minimized subject to these constraints here. And it turns out that when we do this, the optimal thing is actually for 16% of the time to be subject to a false positive rate of 0, which basically means nobody is going to be deemed positive. So we're throwing out 17% of the people, and the remainder we're subjecting to a false positive rate of 39.6%. So I don't know how people would feel about that, but that's another way of dropping down to the ROC curve, which is what's of group 2, which is what's required by the rather demanding equal odds measure of justice that some people like. Well, what about inaccuracy with a threshold equality constraint? So let's set that up. It's simple to set up. The threshold for group 1 has to be the same as the threshold for group 2. Let's find out when that would actually happen. Those are the false positive rates that would create that equality. So just to illustrate, supposing the false positive rate for group 1 was 57%, we could then see, well, that means that the false positive rate, if you want threshold equality, for group 2 must be 42%. And now what we can do is to minimize our objective function subject to our standard constraints and our threshold equality constraints. So what we get is the following, and you can see that inaccuracy costs did go up a little bit, but not too badly. However, what you can also see is look at the difference in the false positive rates and the true positive rates that result from an equal standard for everybody. For group 1, 27% of their unqualifieds are being admitted, whereas only 17% of group 2. And among group 1, 83.4% of those who would succeed are being classified as positive, whereas for group 2, even though the incidence is the same, only 55.2% are being classified as positive. So that's one of the things that creates the concern that a threshold measure of equality, threshold equality, can actually result in some pretty problematic distinctions among the two groups. So let's summarize our result. I'm going to have some little functions here that help us. You can ignore that. I think like you could ignore that. That's just getting some data in the right form. And let's make our little data set here that summarizes our results. And I'm going to need to move that a little bit that way for you to see it. Okay. There we go. Just enough room for you to see. Okay, so let's orient ourselves to this chart. We have our 6 scenarios here. No constraints. Insist on false positive uniformity. Demographic parity, meaning positive rates are equal, see 0.6347, 0.6347. False positive rate uniformity, 0.253, 0.253. Unconstrained, numbers can vary all over the place. Equal opportunity means the true positive rates are the same. Equal odds means the false positive rate and the true positive rate is the same. And equal threshold means that the threshold is the same. And so we can compare, for example, the inaccuracy costs that result from each of these regimes, and we can see that really they're pretty similar. Yeah, equal threshold does drive it up a bit, and the one outlier is equal odds, which, as I've talked about, by forcing group 1 to drop down to group 2's ROC curve, greatly increases the costs of inaccuracy. We can also see that in general the threshold is going to be much different under these measures, except of course for the equal threshold requirement. And we can see the discrimination that we've talked about in that the false positive and true positive rates tend to be different in group 1 and group 2 in many of these scenarios. So what we see is that, at least in this example, inaccuracy costs are not disturbed greatly by imposing false positive uniformity, by imposing demographic parity, or equal opportunity. Imposition of an equal threshold does raise inaccuracy costs somewhat, but not in a fashion that would disturb many people. Right? Difference there. The one criteria that causes problems, because again it forces group 1 to work on group 2's ROC curve, is equal odds, which really does increase those inaccuracy costs. You'll also notice that, except in the case of equal threshold, however, the inaccuracy cost minimizing threshold for group 1 in this set of scenarios is higher than it is for group 2, and that's suggesting that some form of what you might call affirmative action actually makes some sense here, not again for any grand reasons of social justice or repression or anything, but just for the sort of conservative goal of minimizing inaccuracy costs. Okay, so that was one experiment. But in fact, there are thousands of experiments we can run within the framework here. For example, we could vary the parameter that determine the ROC curves of the two groups. We could vary the parameter that determine the relationship between threshold and false positive rate for the groups. We could vary the cost ratio. We could vary the incidence of the positive class among both groups. There are lots and lots of combinations. Now, I am not going to tackle every permutation here. That would make this essay and the video unbelievably long instead of just really long. But what we can do is sample from a few scenarios to get a sense of how sensitive our results are to the particular parameters selected. To do this, I'm going to turn all that coding that you saw in the prior section into a giant Wolfram language function, and then we're going to explore 8 different scenarios. You definitely do not need to read this code. It's here as a reference. We are now going to run it down to here. All right, and let's just look at this final code here, and it may still be inscrutable. But the idea is, remember we produced that data set up here? We're going to automate that process where basically I give the machine the cost ratios, the fraction of the population that's in the minority, the incidence among group 1 and group 2 of the positive class, the ROC curves for each group, and the threshold functions for each group. I'm also going to label a bunch of scenarios, and then if I need to push options to the data set that's ultimately going to wrap this all up, I can do that here. So that's what this code is doing here. I do want to check at various points whether two numbers are very, very close to each other. So that's a function here. And I also write a little function that makes sure that my data set makes sense. So I'm going to make sure, for example, that if in the demographic parity line, that in fact the positive rate is equal for both groups, or that in the equal threshold line, the thresholds are equal. So that's what that code's about. And finally, I've got one more visualization function, which is going to take the rows of our data set, and it's going to produce these radial axis plots, sometimes called radar plots, from that, which will help us understand what's going on. So the first experiment isn't going to add any new information. It's really just making sure this code works. So here we are. Let's just orient ourselves to the code. This means that the cost ratio for both groups is 2. The incidence of the minority group, I'm sorry, not the incidence, the fraction of the population that's in the minority group is 20%. The incidence of the positive class in both groups is 70%. They're working from group 1 is subject to the ROC1 ROC curve. Group 2 uses the ROC2 ROC curve. We have T1 and T2 as the thresholds, and scenario 6 is just a listing of labels for each of the scenarios that we're going to run, and these are in fact the formatting code that I'm pushing to the data set. So let's see how long it takes to do that whole experiment, and I think that's pretty cool. So what do we see here? Well, we're going to see the false positive rate, true positive rate, accuracy, and threshold among group 1, same stats among group 2, and the total costs of inaccuracy. And we can validate that this data is sensible. That's good. And I've done some hand checking, and it does seem like this is exactly what I got before, so I'm feeling good about my function. The other thing we might want to look at is this little radar plot where I've got these 5 things to look at for each group: the false positive rate, true positive rate, accuracy, and threshold for each group. Blue is group 1, orange is group 2. Here's what things look like in the unconstrained case, and you can see, for example, that the false positive rate for group 2 is higher than for group 1, but the true positive rate is higher for group 1 than for group 2. Positive rate's about the same, accuracy higher for group 1. But we could also say, hey, what about in the equal opportunity setting? And we see in the equal opportunity setting, the true positive rate is, as it should be, exactly equal. Now the false positive rate for group 2 is bigger than for group 1. The accuracy is still higher for group 1 than for group 2, etc. Let's one more to illustrate. Here's the equal threshold requirement, and you can see that while the threshold is equal, the other metrics, group 2 is inferior in all other metrics, and this is what gives rise to the concern about use of equal thresholds, is that even in scenarios where the incidence is the same, if the ROC curve for group 2 is lower than the ROC curve for group 1, you can get into real problems. All right, so that's our radar plot. That's available to you to explore. I think it's a useful visualization. Okay, let's do some more experiments. In this experiment, all I'm going to change is the cost ratio. Maybe all these weird things that are a result of having an asymmetric cost ratio, where having a false positive costs more than having a false negative. Let's see. And if you look at this, you're going to see that it really, well, first of all, let's make sure this makes sense. It does. We can generate our radar plot if we want to explore things further. But the bottom line is that although the individual numbers change a little bit, the overall result is the same. We're going to see, for example, higher accuracy again in group 1 than group 2. We're going to see very different optimal thresholds in group 1 and group 2, except when we force the threshold to be the same. And we're generally going to see different false positive rates and true positive rates, except, for example, in equal odds, where we're going to force them to be equal. You're going to see that the costs of moving to these different realms of justice do not actually increase inaccuracy costs very much in this scenario, with the one exception being equal odds, and I won't repeat why equal odds does that. Okay, that's experiment 1. Well, what about experiment 2? Experiment 2, I'm going to keep everything from experiment 1, but I want to see what happens when the incidence in the group 1 is actually higher than it is in group 2, for whatever reason. Maybe there's no causal relationship, but maybe because, for example, members of group 2 tend to be poor, that and poverty does relate to probability of success, inversely, that they end up doing, the minorities end up doing more poorly. So that's what I've set up here, and you'll notice that I've maximized the entropy of the distribution of class among the minority. At 0.5, it's very hard to guess, whereas I've made it easier for the majority, for group 1, by giving them an incidence that's closer to either 1 or 0. Remember that entropy is low as the probabilities approach 0 or 1, and it peaks as the probability approaches 0.5. So here, the majority has sort of two advantages. One is higher incidence, and the other is lower initial entropy. So what we see is, again, accuracy greater among group 1 than group 2. We see some significant differences in the threshold, except when we force it to be equal. We see that the true positive rate for group 1 is higher than it is for group 2, except when we force them to be the same as it is in equal opportunity and in equal odds. And we see that the false positive rate it varies, doesn't it, from case to case here. So let's look at inaccuracy costs. What we see is the story we've seen before, which is changing to most of these regimes of justice doesn't bump up inaccuracy costs greatly. What it does do, with the exception, though, of equal odds, where equal odds, again, results in significant increases in inaccuracy costs. I guess I should make sure that this all worked. It did, or at least I didn't detect any obvious issues. And here's our radar plot, and we can go through and look at the effects of different justice constraints on these 5 measured statistics relating to the classification. Okay? So that's experiment 2. What about experiment 3? I'm going to keep, experiment 3 differs from experiment 2 only in that now I'm going to give the minority the benefit of lower entropy. Yes, the majority still has higher incidence, but it's closer to the middle. It's going to be harder to classify them than it is among group 2. So let's run it. And what do we see? We see the discrimination that we've seen before persist somewhat in that, for example, true positive rates can differ among the two classes. For example, unconstrained, we have a, 53 percentage point difference in the true positive rate, even though there's really only a 25% percentage point difference in the actual incidence. But we also see that the inaccuracy costs are going up in a number of the scenarios now. Now, moving to demographic parity actually results in a substantial increase in inaccuracy costs. Equal opportunity has a significant effect, and equal odds now really has a big effect of increasing inaccuracy costs by 40%. So one of the things we're learning already is that the effect of moving to different metrics of justice depends on our initial conditions and things like, well, what's the incidence of the positive class in the majority versus the incidence in the minority? And that can make a substantial difference in how the costs of inaccuracy play out. Again, we should verify this experiment worked, And again, if we wanted to, here's a resource available for you to check on the statistics associated with each of these justice regimes. Okay, experiment 4. Let's go back to experiment 1. The only change I'm going to make, though, is now I'm going to elevate the classifier. I'm going to elevate the performance of the classifier on group 2 to be the same as it is on group 1. Okay, so let's see what happens. The results are pretty dramatic here. Everything's essentially the same. That is, the discrimination has been cured almost 100% by simply fixing the classifier's performance on group 2. Maybe we got some better data that enabled us to perform better, and we got some more data that enabled it to perform better. But we can see that it's the difference in ROC curves that has been playing a very substantial role in the different false positive rates, true positive rates, etc. that we've seen. The only thing that's different, though, is that in order to make this all work, the threshold still has to be different. The one exception, of course, is when I force the threshold to be the same in the equal threshold regime, and that has two consequences. The first is that now we actually have driven up inaccuracy costs by requiring the threshold to be the same, even though the relationship between threshold and false positive rate is different, and that's cascaded into now we're back into the realm of discrimination, where the false positive rate and true positive rate for group 1 are different than they are for group 2. But what we can see is that it's the lower ROC curve that's been responsible for an awful lot of what we've been seeing. We should make sure that this experiment makes sense, and again, if we wanted a radar function. Okay, well, how about instead of making the ROC curves the same, let's make the threshold functions the same for both groups. We're going to basically calibrate their classifiers similarly. So we do that. And now we're back looking at something very similar to experiment 1. The gap in thresholds is a little smaller than it was in experiment 1, but otherwise it's the same flavor. And so changing the calibration of the classifiers does not have a real large effect on relieving the problem of discrimination that can exist as a result of having different ROC curves. Well, maybe you've guessed where I'm heading. What if we made basically everything the same? Cost ratios the same. That's the fraction of minorities. Incidence the same. ROC curves the same. Thresholds the same. Let's see if there's still anything sort of sneakily inside the data, lurking in the data, that's going to result in differences between group 1 and group 2. And there isn't. Now we've fixed it. If we could just have the ROC curve be the same for both groups, and the thresholding be the same for both groups, then if the groups are the same, then the classifier is going to treat them equally. So it's useful to see that, in fact, we can achieve equality, but it's going to require some fiddling with the classifier and the calibration of the classifier. And again, here is our this is experiment 6. All right, let's just fix that. Let's make sure experiment 6 is good. And now let's make sure experiment 6, yeah, I feel much better now. Now the orange line is beneath the blue line, so you can't see it, but that's telling us that it's all exactly the same. Okay, I feel better. Experiment 7. What if the ROC curve's the same? The classifier works just as well in each group. Calibration's the same, they're same thresholding. The only thing that's different between the two groups is the incidence of the positive class. 0.75 for group 1, 0.5 for group 2. And what we see is that we do now have what you could call discrimination. That is, the false positive rates and true positive rates are higher in the unconstrained case for group 1 than group 2. The positive rate is often going to be different for group 1 and group 2, and that's true even with equal odds. The positive rate's higher for group 1 because there are more people in the true positive class than in group 2. The other thing we see is that the one thing that causes inaccuracy costs to jump by maybe 10-12% is the requirement of demographic parity, that we get the same positive rate for both groups, even though the true incidence for group 1 is considerably higher for group 2. And so distorting it so that you get the same outcome in both groups creates some significant inaccuracy costs. Again, we should make sure that it all works. It does, thank goodness. And if we want to see things visually, we can. Okay, final thing for symmetry, which is, supposing the ROC curves are the same, but the incidence is different and the calibration is different, what happens then? And it's really not very much different than experiment 7. The optimal threshold for group 2 in each scenario is lower than in experiment 7, but basically we're seeing the same kind of pattern with respect to inaccuracy costs, where it's only demographic parity that is really going to drive up inaccuracy costs. It works. If you want to study it further, there's your radar plot. And you will be pleased to know that the full-length feature film is now over. What we did here, though, is I built on the previous work on classifiers to develop a framework for understanding the discriminatory effects of classification, the ways in which those effects can be reduced, and the cost of doing so. And I would just caution people working in this field that it's actually a complex phenomenon in which details matter, like, is the threshold curve the same? Is the incidence the same? And generalizations are somewhat challenging. But I would say the work has important implications. It gives you an analytic basis for understanding various programs that might be designed to improve the opportunities available to minorities subject to classification. And, as I'm going to show in the next video, which will be considerably shorter, it's going to make it easier to explain the discrimination that we see being apparently caused by certain classifiers. In the next video, I'm going to discuss one that was used to determine parole in prison. So my main hope here is that the essay encourages you to think about discrimination by classifiers, which I do believe is going to be a major issue in the years to come, to think about implications for equal protection, and if anyone's ambitious, to think about ways in which the model could be made yet more complex, or I suppose simpler, in order to get a better handle on what's going on with supervised machine learning operating on real-world problems. Thanks for your attention.